Welcome back to Sleepy Orbits. The house is dark, the hour is late, and your clock, wherever it sits, is ticking off seconds that feel absolute, one after another, the same for everyone, everywhere, forever. Tonight, gently, we're going to take that idea apart. Tonight, we're going to visit a place where a second is not second. 28,000 light years away in a crowded ball of ancient stars, there is a dead sun the size of a city that spins 716 times every second, not 716 times a minute, a second. Its equator moves at nearly a quarter of the speed of light. It has been spinning this way for billions of years, and around it, according to the same physics that runs your phone's navigation, space itself is being dragged, swirled around the star like water around a closing drain. And time on and near that star runs measurably, provably differently than it runs in your bedroom. You've probably heard that time slows near black holes, that gravity bends the clock, and you may think of it as exotic trivia from the far side of the universe. But here's the thing most people don't realize. Time has no master copy, not out there and not here. The clock effects we'll meet tonight have been measured around our own planet by satellites you rely on every day, and the strange spinning star we're traveling to is simply the place where the universe turns the volume up, where the quiet truth about time becomes impossible to ignore. Tonight, we'll meet the fastest clock in nature, learn what it does to the space around it, and follow the story of the century of clever people who caught time bending, first by fractions of a second, then by whole worlds. And somewhere along the way, the second ticking beside your bed is going to become both less solid and more precious than it was when you lay down. Now, let's begin. Let's start at the record holder, because everything tonight orbits it. In the southern constellation, Sagittarius, toward the crowded heart of our galaxy, there is a globular cluster called Terzan 5, a swarm of 1 million ancient stars packed into a ball a few dozen light years wide, one of the densest neighborhoods the Milky Way owns. And in November of 2004, a young astronomer named Jason Hessels, sifting radio data from the Great Dish at Green Bank, found something in that swarm that beat every clock humanity had ever pointed at the sky. A pulsar, a spinning dead star, flashing its radio beam across the Earth 716 times per second. The number is easy to say and almost impossible to hold. 716 full rotations of an entire star every second, 43,000 revolutions per minute, faster than the blades of a kitchen blender, faster than the crankshaft of a racing engine at red line, except the thing turning is not a blade or a shaft. It is a star, a full sun, and a half of matter compressed, as we've learned on other nights, into a sphere perhaps 25 kilometers across, the size of a city, dense beyond all metaphor. And it is turning over 700 times between each beat of your resting heart. Its equator, to complete a lap that fast, moves at roughly 70,000 kilometers per second, about a quarter of the speed of light, the fastest surface of any known object in the universe. And here is the detail I want to tuck beside your pillow at the top of the night. 716 cycles per second is not just a rotation rate, it's a pitch. Frequencies in that range are sound to human ears, and if the vacuum of space could carry the vibration to you, the spinning of this star would be a note, a clear, high tone near the top of a piano's treble range, 2.5 octaves above middle C. There is a star in Sagittarius, older than our sun, heavier than our sun, that has been singing one high note perfectly, without breath, for billions of years. Tonight, we're going to sit close enough to hear what that note does to time. But before we can watch time bend, we have to agree on what time is. And the honest answer, the physicist's answer, is humbler than you'd expect and stranger than you'd like. Nobody has ever measured time. Not once, not anywhere. What we measure, always, is change. And the steadier the change, the better the clock. A swinging pendulum, a vibrating crystal, the earth turning against the stars, a cesium atom in the vaults of the Standards Institutes, absorbing microwaves that flick it between two energy states at a rate so steady that humanity simply gave up on the heavens and redefined the second itself. Since the 1960s, as a fixed count of those atomic flickers, billions of them per tick. A clock, any clock, your wristwatch, your heartbeat, the cesium fountain in Paris is just a thing that repeats reliably, plus a counter. That's all time has ever been operationally counted repetition, and for most of scientific history, everyone assumed the counting ran at one universal rate, a great invisible metronome behind the universe, Newton's absolute time, flowing equably, everywhere, regardless of anything. It was the most reasonable assumption ever made, and it is wrong. The unraveling came in two blows, both from the same young patent clerk, and both, at heart, are ideas simple enough for the edge of sleep. The first, in 1905, came from taking one experimental fact with total seriousness. Light always moves at the same speed, no matter how you chase it. Follow that stubborn fact to its conclusions and something has to give, and what gives is simultaneity, the universal now. Two events that happen at the same moment for you do not happen at the same moment for someone moving past you, not as an illusion or a delay of signals, but truly in the deep bookkeeping of reality. Motion mixes a little space into your time and a little time into your space, and clocks that move fast run slow, genuinely slow, relative to those that stay home. The second blow, 10 years later, was gravity's turn. General relativity recast gravity as geometry, mass bending the shape of space and time together. And one of its first predictions was that clocks deep in gravity's wells run slower than clocks above them. Not seem slower, run slower. Time near a mass is literally a different, more leisurely quantity than time far away, and every mass does it. Planets, stars, your own body, faintly. The way every stone dropped in a pond makes ripples, however small. And here's what makes tonight's subject a bedtime story rather than a lecture. All of this is measured daily, boringly, by machinery your life already depends on. The clearest example flies over your roof right now. The satellites of the global positioning system carry atomic clocks, and those clocks are in two of time's strange regimes at once, moving fast, which slows them, and orbiting high above Earth's gravity well, which speeds them, and the two effects don't cancel. Net result, the satellite clocks run fast by about 38 millionths of a second per day compared to clocks on the ground. 38 millionths sounds like nothing, but position is computed from light travel times, and light covers 300 meters in a millionth of a second, so an uncorrected day of relativity would smear every map on Earth by kilometers, and within weeks navigation would be useless. The engineers knew, so the clocks are built deliberately wrong on the ground, tuned slow, so that once in orbit, with time itself running differently up there, they tick perfectly. Sit with that for a second. Your phone finds the coffee shop because somebody corrected for the bending of time. Einstein's strangest ideas are not out among the black holes. They're in your pocket, on your dashboard, quietly consulted every time you ask a machine where you are. Time really does run at different rates in different places, here, today, around this ordinary planet. And the only reason you've never noticed is that Earth is a shallow well and a slow spinner, and the differences are millionths. Tonight's destination is what happens when the well is deep, and the spin is 716 per second, and the millionths become the whole story. Now let's build the deep well, and regular travelers of these nights can walk this part with me like an old road, because the neutron star is a friend of the channel by now, though tonight we'll meet it from a new side, the side that keeps time. You know the recipe. A giant star dies, its core collapses, and if the core is heavy enough to crush atoms but not quite heavy enough to fall out of the universe entirely, it lands on the ladder's second rung, a neutron star, a sun and a half of matter in a city-sized sphere, matter so dense a teaspoon outweighs a mountain range, gravity at the surface, billions of times ours. On our museum night, we met its violent cousins, and on our black hole night, we treated it as the last stop before the abyss. Tonight, look at it instead as a place where time itself thickens. Because that surface gravity is not just a crushing force, it is, by Einstein's geometry, a depth. A neutron star sits in a gravity well second only to a black hole's, and down in that well the clocks genuinely crawl. The numbers are not subtle. On the surface of a typical neutron star, time runs something like 20 to 30% slower than it does out here in the shallow universe. Live a year there, by your own faithful wristwatch, your own heartbeat, your own aging cells, And when you climbed back out, you would find the rest of the cosmos had run around 15 or 16 months in your absence. The exchange rate between a neutron star's time and ours is roughly 4 years, theirs to 5 years ours, a discount on existence applied at the door by mass alone. And I want to be careful here about what this means, because the phrase "time runs slower" invites a mistake. The mistake of imagining molasses, of imagining that on the neutron star everything would feel sluggish, thoughts dragging, clocks visibly laboring. No, this is the most important sentence of the night, and it's also, I think, the most calming one. Time always feels normal from inside. Down on that impossible surface, your watch would tick its familiar tick. Your heart would keep its familiar rhythm. A second would feel exactly like this second, the one you're inside right now. Nothing local would seem wrong at all. The slowness only exists in the comparison, only appears when two regions of the universe check their ledgers against each other, when light climbs out of the well and arrives stretched, when the traveler returns and the calendars disagree. Proper time, the physicists call it, the time you carry with you, and everyone's proper time is always, everywhere, perfectly proper. The universe never robs anyone of their seconds. It just declines, politely and permanently, to keep them synchronized. There is no master clock hanging behind the stars, no great metronome the neutron star is falling behind. There are only clocks, billions upon billions of them, every atom one of them, each keeping perfect faith with its own path through the geometry. And the deep discovery of the last century is that the paths themselves are what differ. Time is not a river we all stand in together. Time is more like a personal stream, one per traveler, and gravity and speed decide how your stream winds compared to mine, and nobody's stream is the real one. Hold on to that as we descend tonight, because everything that follows, the dragging, the swirling, the fractured second at the equator of the spinning star, is going to sound like time breaking. It never breaks. It just stops pretending to be shared. The story of how we found nature's great clocks deserves its few minutes, because it's one of the best discovery tales in all of science. And it begins with a 24-year-old graduate student and a field full of wire. Cambridge, England, 1967. Jocelyn Bell, a young radio astronomer from Northern Ireland, had spent 2 years helping to build, by hand with hammers and pliers, a 4-acre radio telescope, a vineyard of poles and cables designed to watch the sky flicker. Her job, once it ran, was to analyze the output, which arrived as pen-drawn squiggles on rolls of chart paper, 96 feet of paper per day, all of it reviewed by eye, hers. And a few months in, she noticed what she famously called a bit of scruff, a patch of squiggle, half an inch of ink among miles of it, that didn't look like a twinkling source and didn't look like human interference, and which, crucially, came back night after night from the same patch of sky 4 minutes earlier each day, which is the signature of something fixed among the stars. When she and her supervisor finally caught it on a faster recorder, the scruff resolved into something no astronomer had ever seen. Pulses. Sharp, regular radio pulses, one every 1.3 seconds, steady as a metronome, from a point in the constellation Vulpecula, a place where nothing visible sat at all. The regularity was the shocking part. Nature, as far as anyone knew, didn't tick. Ticking meant machinery, and machinery meant, well, the team allowed themselves the joke that history has kept. They labeled the source LGM1, Little Green Men 1, and for a few strange weeks the possibility was taken half seriously until Bell, reviewing miles more chart paper, found a second ticking source in a different corner of the sky, and then a third and fourth. Whatever ticked, the universe was full of them, and no committee of civilizations coordinates their beacons like that. It was nature, after all, ticking. The papers announced pulsars, pulsating radio sources, and within a year theorists had converged on the only machinery extreme enough to keep that beat, a spinning neutron star, its magnetic poles firing lighthouse beams of radio into the dark, sweeping past Earth once per rotation. The impossible objects predicted in the 1930s were real, and they announced themselves not with an explosion but with a pulse, a tick, a clock signal, the universe's own timekeeping arriving on chart paper in a Cambridge field. The Nobel Prize followed in 1974 and went, notoriously, to the supervisor and not to the young woman who built the instrument and found the scruff, an omission argued about ever since, and worn by Bell herself over a long and decorated career, with a grace that has become its own kind of legend. She has said more than once that she's done rather well out of not winning it. History, for its part, has quietly reassigned the credit. Why does this story open tonight's second act? Because of what pulsars turned out to be for. In the decades after Bell's scruff, astronomers timed these objects and slowly realized they'd been handed something almost unbelievable. A pulsar is a clock, a natural clock of astonishing quality. A spinning sphere of a sun and a half of matter has colossal rotational inertia. Nothing can hurry it. Nothing can casually slow it. It spins because it spins because it spins, shedding its energy so gradually that its period drifts by less than a second over millions of years. And that drift itself is smooth and predictable to exquisite precision. Time the pulses for a few years and you can predict the arrival of a pulse years further on to within millionths of a second. The universe, it turned out, is furnished with clocks, free-floating, indestructible, visible across thousands of light years, and they are made, of all things, from the collapsed hearts of catastrophes, the same objects our museum night filed under violence. The best timekeepers in nature are dead stars. And that discovery set up tonight's central irony, the one the whole night turns on. The finest clocks in existence live in the deepest wells and the fastest spins, exactly where time itself refuses to run at the standard rate. Nature keeps its most perfect time in the places where time is least shared. And the story of the last 50 years of this science is the story of learning to read those clocks so precisely that their errors, their tiny relativistic errors, became the message. There's a coda to the discovery story worth savoring before we move on, because within 2 years of Bell's scruff, the new objects delivered a moment of pure theatre, and it remains one of the few times in history that human beings have watched, with something close to their own eyes, a star keeping time. The question hanging over the young pulsar science was whether the radio ticks had counterparts in ordinary light, and the obvious candidate was the corpse expected at the heart of the Crab Nebula, the wreck of the 1054 guest star our museum night visited. In January of 1969, astronomers at an observatory in Arizona pointed a telescope at the modest-looking star at the nebula's center, fed its light not to a camera, but to a fast photoelectric detector. And there it was. The star was blinking. 30 times a second, flash, 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 a visible star strobing like faulty neon, its light switching on and off faster than human vision can separate, which is precisely why no one had ever noticed. To the eye and to every photograph, the flicker smears into a steady, calm point, and the crab's heart had sat in plain sight in telescopes for 2 centuries, ticking, unread. The teams that caught it described the room going quiet as the oscilloscope trace resolved into clean pulses, one astronomer reportedly muttering that a star simply had no business doing that. But it did, and it does, tonight. 30 times between each beat of your heart, and there's a wonderful detail buried in the arithmetic. 30 flashes per second sits just past the threshold where human vision fuses flicker into continuity. The same threshold that makes cinema work, films run at 24 frames. The Crab pulsar is strobing at very nearly the boundary of what a human eye could, under perfect conditions, almost perceive. The universe's showpiece clock ticking just barely too fast for the animal watching it, as if the projector of the world ran 1 notch above our frame rate. Slow the star by a factor of 2, and observers with sharp eyes might genuinely see the youngest famous pulsar in the sky as what it is, a lighthouse. Instead, it hides in its own speed, steady to us, frantic in truth, and I can think of no better emblem for tonight's whole subject, time, everywhere, doing far more than the senses reading it were built to notice. Which raises the question of our record holder, because ordinary pulsars, fresh from their supernovae, spin a few times a second at most, and slow down from there. 716 per second is not a birth speed, it's a second life. And the story of how a dead star gets one is worth telling slowly, because it may be the best resurrection tale in astrophysics. They're called millisecond pulsars, the elite class our record holder leads, and the clue to their origin is company. Almost every one of them has, or had, a companion star. Here's the biography. A pulsar is born in the usual fire, spins its youthful spin, and then does what all pulsars do. It broadcasts its rotation away, slowing across tens of millions of years. Its pulses, stretching its lighthouse, dimming until somewhere below 1 rotation per second, the machinery fails. The beams gutter out, and the object crosses what astronomers actually call the death line into the graveyard population, a dark, silent, spinning ember finished, as far as anyone watching could tell, forever. Most stay finished, but if the dead pulsar has a partner, an ordinary star in a close orbit, then patience changes everything, because stars age, and when the companion eventually swells into its red giant phase, its outer layers spill toward the corpse. And falling matter, as we learned at the feeding black holes, doesn't fall straight. It spirals, forming a disk, and the disk doesn't just heat and glow, it pushes. Every parcel of gas that lands on the dead star's surface arrives with sideways motion, a tiny twist of angular momentum, delivered like a finger flicking the rim of a stopped wheel. One flick does nothing. But the companion pours its substance across the gap for hundreds of millions of years, flick after flick after flick, quadrillions of tons of spiraling gas, and slowly, magnificently, the corpse begins to turn faster. 10 rotations a second, 100, 500. The dead star spins up, reignites its beams, and returns from the graveyard transformed. No longer the heavy, slow toll of a young pulsar, but a shriek, a hum, a note, 700 times a second, reborn with a rotation it could never have had in its first life, and stabilized by that colossal spin into the best clock nature knows how to make. Astronomers call the process recycling, which is far too municipal a word for what it is. It is a dead star drinking from a living one until it wakes up singing. And the companion pays for it, which adds the note of quiet tragedy these stories always seem to carry. In many systems, the giving star is consumed nearly whole, whittled across the eons to a planet-sized cinder of a core, and in the extreme cases, the reborn pulsar's own radiation then turns on its benefactor, its beams and winds, slowly eroding what remains of the star that resurrected it. Astronomers, who name things more mischievously than you'd guess, call these systems black widows and redbacks after the spiders, and the fastest spinners tend to be found in exactly such systems, or in the crowded hearts of globular clusters like Terzan 5, where dead stars can capture new partners again and again. Our record holder lives in precisely that kind of dense, stellar city, and it has a companion still, a bloated little star that regularly eclipses the pulsar's beam from our point of view, the surviving witness and probable donor of the spin-up. So, when you picture the fastest rotor in the universe tonight, picture the whole story around it. A star that died before our sun was born, a silence that lasted eons, a slow feast measured in geological ages, and now a city-sized sphere humming its high note in a swarm of 1,000,000 ancient suns wearing a rotation it was given, tick by tick, by a partner it has nearly used up. The universe's best clocks are not merely found. They are made, slowly, in pairs, out of death and patience and theft, which seems, at this hour of the night, about right for anything that keeps perfect time. Now we're ready for tonight's centerpiece, the effect the whole night is named for, and I want to introduce it the way it was introduced to the world, which is to say, almost apologetically, as a footnote nobody expected to matter. In 1918, barely 2 years after Einstein published General Relativity, two Austrian physicists, Joseph Lenzer and Hans Thirring, sat down with the new equations and asked a modest question. Newton's gravity cared only about mass and distance. A spinning planet pulled exactly like a still one. Did Einstein's? They worked through the mathematics and found the answer was no. In general relativity, a rotating mass does something a static one does not. It drags. The spinning body communicates its rotation to the geometry around it, twisting space-time itself into a slow circulation, so that the space near a rotating planet or star is not a still stage but a moving one, wheeling around the body in the direction of its spin, strongly nearby, weakly farther out, the way water circles a stirred cup. The pair computed the size of the effect for Earth and found it so vanishingly small, fractions of an arc-second per century in the orbits of moons, that it was filed away as a theoretical curiosity, beautiful, true if relativity was true, and forever beyond measurement. The universe, in their equations, was a fluid you could stir. It's just that nothing anyone knew of stirred it hard enough to notice. Let me give you the honest picture of what frame dragging means, because it's subtler and stranger than the whirlpool image alone, and the strangeness is the point. Imagine you're floating near a massive, spinning body, and you do the most innocent thing in physics. You try to stay still. Not orbit, just hover, fixed, pointing at a distant star, the very definition of not rotating. Near a spinning mass, you will find that you can't, not quite, because still is no longer a thing the local universe agrees about. The space you're floating in is itself circulating, and to hold your position against the distant stars you must constantly fight a gentle, carrying current, like a swimmer treading water in a slowly rotating pool. Let go, relax completely, give the universe no input at all, and you begin, imperceptibly at first, to be carried around the body, not pushed by any force you can feel, not pulled by anything you could shield against, but conveyed, because the very definition of staying put has been set, turning beneath you. Gyroscopes make the effect concrete. A gyroscope's whole job is to point one way forever. It is the universe's memory of direction, and near a rotating mass, a perfect gyroscope, subject to no force whatsoever, slowly changes where it points, precessing around the spin of the body it hovers near, because the directions themselves, the north, south, east, west of the local geometry, are being wheeled around like chalk lines on a turning carousel. Nothing touches the gyroscope. The floor it's standing on is what turns, and the floor is space. That's frame dragging, the discovery that rotation is contagious, that a spinning mass does not merely sit in space and time, but grips them, winds them, spends its rotation into the geometry around it. Mass tells space-time how to curve, goes the old summary of Einstein's theory. Lenser and Thirring added the quieter clause that took a century to hear properly. Spin tells space-time how to turn. For most of a century, that's where the matter rested. A beautiful clause nobody could check, and the story of how it was finally checked is one of the great sagas of experimental patience, arguably the most stubborn physics experiment ever flown. It's called Gravity Probe B, and it began, as tonight's stories tend to, with an audacious question asked over lunch. In the late 1950s at Stanford, physicists began wondering whether the new art of spaceflight could test Einstein's subtlest predictions directly, and by 1960 the plan existed on paper. Put perfect gyroscopes in orbit around the Earth, point them at a distant star, and simply watch, for months, whether the directions they hold drift in the two ways relativity demands, a larger tilt from the curvature of Earth's gravity well, and a far smaller twist, the lens-Thirring twist, from our planet's rotation dragging its surrounding space around with it. The whirlpool clause, measured not at some monster star, but here, around the spinning Earth itself. The plan was simple. The requirements were absurd. The frame-dragging signal at orbit height amounts to a drift of 39 thousandths of an arc-second per year, an angle equivalent to the width of a human hair, seen from something like 15 kilometers away, accumulating over a full year, and any imperfection in the gyroscopes, any lump, any wobble, any stray electric or magnetic whisper would swamp it a millionfold. So they set out to build the most perfect objects ever made, and decades later, they had. The heart of Gravity Probe B was 4 spheres of fused quartz, each the size of a ping-pong ball, ground and polished until they were round to within about 40 atoms. 40 atoms. Scaled to the size of the Earth, the tallest mountain on such a sphere would stand about 2 meters high. Coated in a whisper of superconducting niobium, suspended in vacuum by electric fields, spun up with jets of helium, and read out by quantum magnetometers, they were, and remain, among the roundest, smoothest, most perfect things our species has ever manufactured, and 4 of them flew to orbit in April of 2004, chilled near absolute zero inside the largest flask of superfluid helium ever sent to space, staring down a telescope at a single guide star. The mission had waited 40 years for launch, surviving cancellation after cancellation, outliving some of its founders. And after launch, it had to wait some more because the data, when it came down, was a nightmare. Tiny, unexpected electrostatic patches on the spheres had introduced wobbles that took an army of analysts 5 further years to untangle. But in May of 2011, half a century after the lunch table idea, the team announced the verdict. The gyroscopes had drifted, both drifts. The big geodetic tilt, the mark of Earth's dent in space-time, measured to a fraction of a percent, matching Einstein. And there, underneath it, dug out of the noise, the small twist. 37 thousandths of an arc second per year against a predicted 39, agreeing within the measurement's precision. The Earth drags space, our planet, this ordinary rock, spinning its ordinary daily spin, measurably wheels the geometry around itself as it turns, and 4 perfect spheres pointing at a star were slowly carried around with it through no force at all, riding the current of a whirlpool 5 decades of physicists had insisted must be there. The rate is gentle beyond imagining at 39 thousandths of an arc second per year. The space around Earth completes 1 full extra turn roughly every 35 million years, a whirlpool that has managed perhaps 130 revolutions since the dinosaurs fell. But it is real, it is measured, and every one of us lives inside it, sleeps inside it, tonight being carried imperceptibly in the direction of sunrise by the turning of the floor of the world. When people say Einstein's strange predictions all came true, this is the one that took the longest and cost the most patience, and it means the stage you're lying on is, very slightly, a carousel. Now, said the astronomers, holding that confirmed clause in their hands, let's go find where the carousel spins fast. Where the carousel spins fast, of course, is around collapsed stars and the confirmation that frame dragging scales up. From Earth's 35 million year whirlpool to something you could watch bend an orbit, arrived in 2020 from a system that might have been designed as a teaching aid. It's called, in the catalogues, J1141. A pair discovered decades ago in the southern sky, a pulsar, ticking its faithful tick in a tight 5-hour orbit around a white dwarf, the Earth-sized ember of a star that died gently. The lucky accident is the order of the deaths. The white dwarf formed first, and in its final act of formation, matter from the dying star's envelope spilled onto it and spun it up ferociously. The same flick-by-flick resurrection physics we met earlier applied to the lighter rung of the ladder. The result is a white dwarf rotating in minutes rather than the stately days such embers usually keep, a planet-sized flywheel, and beside it a pulsar clock ticking with microsecond fidelity. A massive spinning body, and next to it the best stopwatch in nature. 2 decades of astronomers using the great dishes at parks in Australia timed that stopwatch through nearly 20 years of orbits, hundreds of thousands of pulses, and slowly, out of the accumulated arithmetic, a strange motion emerged. The orbit is tumbling. The plane of the pulsar's path around the white dwarf is tilting, precessing through space, wheeling slowly around like a coin wobbling on a table. And when the team subtracted every known effect, The tidal, the classical, the ordinary, relativistic. A residue remained, a slow drift of the orbit's orientation that matched, in size and direction, exactly one thing: frame dragging. The white dwarf's furious spin is stirring the space it sits in, and the pulsar's entire orbit, tens of thousands of kilometers of it, is being carried around in the current, the whole racetrack slowly rotating because the spinning mass at its center refuses to leave the surrounding geometry alone. The paper landed in the journal Science in January of 2020, a century and 2 years after Lindsay and Thirring apologized for the smallness of their effect. Around Earth, the whirlpool turns once in 35 million years, and it took 40 years and 4 perfect spheres to catch it. Around a spun-up white dwarf, it visibly reorients an orbit within a human career. And both of those, tonight's whole journey insists, are the gentle cases. The dial goes further. We've now confirmed the stirring around a spinning planet and around a spinning ember. What remains is to stand carefully in imagination beside the fastest spinning massive object the universe is known to hold, and watch what the same clause of the same equations does there. Everything so far has been the shallow end. Come on then. Terzan 5 is waiting, and the note is getting louder. So board the impossible ship one more time and let's make the approach properly, because the setting alone is worth the trip. Terzan 5 is not a quiet suburb like ours. As you close in, the sky itself begins to crowd, stars thickening from the familiar sparse scatter into a glittering fog. A million suns packed into a ball you could cross at light speed in decades. Ancient stars, most of them, ambers and golds, so dense near the core that neighboring systems sit light days apart rather than light years, and any world here would know no true night, only a ceiling of thousands of brilliant lamps. This is the kind of neighborhood where dead stars find new partners, the dance hall physics that builds millisecond pulsars, and somewhere in the thick of it, your instruments lock onto the record holder. You will not see it, not really. A 25-kilometer sphere at any respectful distance is a point, but you can see what it does. The radio beam sweeps past you 716 times a second, far too fast to perceive as pulses, blurring instead into that continuous, eerie tone. And as you drift closer, edging down toward the deep well, the strangeness begins, not with violence, but with a series of quiet refusals. Your navigation begins refusing to hold station. You've asked the ship to hover, fixed, relative to the distant cluster stars, and the ship reports correctly that it cannot, not without continuous correction, because the space you occupy is circulating. The whirlpool claws at full volume now, and everything at your radius is being carried around the star in the direction of its spin. Cut the engines, surrender, and you become a leaf in it, swept into a slow, involuntary orbit, not falling toward the star, simply carried around it, by nothing, by geometry, by the current in the nothing. Your gyroscope's next. The faithful little memories of direction begin to wheel, all of them together, in stately agreement, their fixed stars no longer fixed, the whole concept of a constant direction dissolving into the swirl, and the closer you edge, the faster the wheel turns until, in the final kilometers above the surface, the dragging approaches the star's own madness, space itself circulating dozens, hundreds of times a second. The geometry blurred around the spinning mass like water flung from a wheel, and to hold your nose pointed at one crater on that impossible surface would require your ship to pirouette hundreds of times each second, which is another way of saying that near the fastest rotor in the universe pointing at a fixed thing has simply stopped being one of the universe's available activities. And still the strangest instrument on the ship is the clock rack. You carry 3 clocks tonight, identical atomic hearts, and you've dispatched 2 of them down the well on probes, one to hover above the star's pole, one to skim low and screaming around its equator, while the third stays with you, high and safe. All 3 tick perfectly. Each, sampled locally, is flawless, proper time, proper everywhere as promised. But the rack compares them continuously across the gulfs, and the comparison is a quiet scandal. The polar clock runs slow against yours, deeply slow. The well's 20-something%, a clock drowned in gravity, aging like a cellared wine. And the equatorial clock runs slower still, noticeably slower than its polar twin, because it carries both burdens at once, the same depth of well, plus the motion, the quarter of light speed sprint of the surface it hugs, and special relativity charges for speed on top of general relativity's charge for depth. 2 clocks on the same star, same distance from its heart, disagreeing with each other because one of them is going for the ride. The star's own equator across the eons has aged less than its own poles. The object is not even a single when. It's a gradient of whens, a body whose middle is measurably younger than its top, spinning fast enough to smear its own present across a detectable range, and it has been doing this, unbothered, since before complex life existed on Earth. This is what the fracture of the second actually looks like up close. No cracks, no drama, no molasses, just clocks, all perfect, all faithful, all irreconcilable, and a universe that sees no problem whatsoever, because it never promised the seconds would match. It only ever promised that yours would be yours. Since we've seen what the deep well does to a neutron star's image from outside, spare a minute for the view from the surface itself, because the same folded geometry, experienced from within, produces one of the strangest skies physics permits, and no night about these objects should end without describing it. Imagine, impossibly, standing on that crust, shielded from everything, and look toward the horizon. On Earth, the horizon is where the ground curves down and away, the planet hiding itself from you beyond a few kilometers. On a neutron star, the light rays that would carry the distant landscape to your eyes are bent, dragged downward along the curvature, hugging the star, and the consequence is that the ground does not disappear beyond a horizon at all. It rises. The landscape curves up around you, visibly, the surface beyond what should be the horizon lifted into view by the bending of its own light, so that standing on the plains of the star, you would seem to stand at the bottom of a vast, shallow bowl, the whole world tilted up toward its rim in every direction, kilometers of gleaming crust that simple geometry says you shouldn't see, served up anyway by the well. Depending on the star's compactness, the effect strengthens toward the theoretical extreme, where the entire far side climbs into view around the rim, a world with no behind, its whole geography visible from any point on it, the bowl closing toward a sphere of landscape wrapped around the sky. And the sky itself pays the complementary price. All the light arriving from the universe above, the million suns of Terzan 5, the distant galaxy, everything is bent inward on its way down to you, concentrated, the full celestial dome compressed into a tightened circle overhead, the stars crowded toward the zenith as if the cosmos had been gathered up like fabric and cinched. Stand there, and the universe is a brilliant, dense disk directly above, ringed by the upturned bowl of the world, and at the edges between the light of stars behind the star, lensed around the limb, smeared into arcs. No eyes will ever stand in that place and confirm it. The gravity forbids the visit more absolutely than any distance we've mourned on other nights. But the geometry is not speculation. It's the same tested bending that NICER reads its radii from, the same clause the clocks obey, and it means the strangest sky in the universe is not above some exotic world at the edge of things. It's above the surface of every neutron star in the catalogue, thousands of them, tonight, each one wearing its bowl of upturned ground and its cinched crown of concentrated heavens, unwitnessed, geometry performing for no audience, the way most of the universe's beauty apparently prefers to work. If tonight's effects still feel like they belong to distant monsters, let me bring the fracture of the second all the way home before we go on, because the most charming experiment in this whole field was performed not at a pulsar, but on a laboratory table, with a stepladder's worth of height. In 2010, physicists at the American Standards Institute in Colorado, keepers of some of the finest atomic clocks ever built, optical clocks so precise they drift less than a second across the age of the universe, ran the homeliest test imaginable. They took two of these clocks, put them in the same room, and raised one of them, relative to the other, by 33 centimeters, about a foot. The height of two stacked shoeboxes, the height difference between your head and your chest as you lie there now. And the raised clock ran fast, measurably, repeatably fast. By the exact whisper, general relativity demands for 33 fewer centimeters of gravity well, a few parts in 100 million billion, a difference that would accumulate to about 1 second's disagreement over several times the age of the universe, and their instruments caught it in a room in Colorado in an afternoon. They ran the companion test too, setting one clock swaying gently, walking pace, and it ran slow, special relativity's toll, also on a tabletop. Time dilation is not a property of neutron stars, it is a property of stairs. Your head, tonight, propped on its pillow, is aging very slightly faster than your feet, and it has been your whole life. The difference amounting, over 90 years, to a few hundred billionths of a second. Your body a quiet little gradient of whens, a Terzan 5 in miniature, too gentle to matter and too real to deny. Every mass makes a well, every well slows the clocks in it, every motion slows them further, and the universe applies the rules with perfect indifference to scale, to a quartz sphere in orbit, to a graduate student's chart paper, to the fastest star in Sagittarius, and to the 30 centimeters between your heart and your ceiling. There is a version of this fact that reads as unsettling, and the internet, as usual, prefers it. But lying where you are, I'd offer the other reading. The laws of the deepest wells and the maddest spins are the same laws running gently through your bedroom, fully tested, fully obeyed, no exceptions found in a century of looking, from 33 centimeters to 28,000 light years. The universe is not divided into a tame region where you live and a lawless one where the monsters do. It's one fabric, one clause, one geometry, stretching without a seam from your pillow to the singing star, and everything on it, everywhere, is keeping its own perfect time. There's a boundary around every spinning pulsar worth pausing at, invisible but absolute, and it answers a question a careful listener might have been holding since we clocked that equator at a quarter of light speed. If the star spins 716 times a second, what about the space above it? The magnetic field lines anchored in the surface, sweeping around with the rotation like spokes of a wheel. A wheel's rim moves faster than its hub. The farther out along the spoke, the faster the sweep. So follow one of those field lines outward from the racing equator, and the co-rotation speed climbs and climbs until, at some radius, simple multiplication says the sweeping field should match the speed of light. That radius has a name, the light cylinder, and for our record holder it sits astonishingly close, only about 66 kilometers from the star's center, barely a few dozen kilometers above the surface. A city-sized star wearing a light speed boundary like a collar. Now, nature does not actually permit the violation. No matter and no signal crosses the light barrier. And what happens at the light cylinder instead is the founding drama of every pulsar's machinery. The magnetic field simply cannot keep up with its own anchor. Inside the cylinder, plasma and field sweep around with the star, co-rotating like a rigid wheel. At the boundary, forced toward the impossible, the field lines can no longer close. They tear open, sweep back, and stream outward, and the particles riding them are flung away in a wind of almost inconceivable power. The pulsar wind accelerated to within a whisker of light speed, carrying the star's rotational energy out into the nebula around it. The crab's glowing wreckage, which we visited among the guest stars, is lit to this day by exactly this, the 1,000-year-old debris energized continuously by the wind pouring off its central pulsar's light cylinder. When you see a photograph of the Crab Nebula glowing, you are seeing the luminous exhaust of a spinning clock, the place where a dead star's rotation, forbidden from dragging its surroundings past the speed of light, pays the difference in radiation and wind. And the beams themselves, the lighthouse flashes that started tonight's whole science, are generated in this same forbidden boundary machinery, which means something quietly poetic. Every pulse Jocelyn Bell found on her chart paper, every tick, every timing array counts tonight, is a message sent from the edge where rotation meets the light barrier, the universe's speed limit enforcing itself 716 times a second and mailing us the receipt. Before the double pulsar takes the stage, its ancestor deserves the introduction, because the first great triumph of pulsar timing happened a generation earlier, and it earned the field its first Nobel Prize, while quietly opening the era our museum night celebrated. In the summer of 1974, at the Great Arecibo Dish in Puerto Rico, a young researcher named Russell Hulse, working through a systematic pulsar survey for his doctorate with his supervisor Joseph Taylor, found a pulsar whose ticks refused to behave. Its period wobbled night after night, speeding and slowing on a repeating 8-hour cycle, and Hulse, initially exasperated, realized the wobble was the oldest signature in astronomy, the Doppler swing of orbital motion. The pulsar was circling something closely and fast, and the arithmetic of its swings revealed the partner to be another neutron star, silent, unseen, the pair whirling around each other every 7 3/4 hours in orbits smaller than our Sun. The first binary pulsar, a clock in orbit around a corpse, and every physicist alive understood the opportunity at the same moment. General relativity makes its boldest prediction for exactly such systems, that two masses whirling in tight orbit must radiate gravitational waves, ripples carrying energy away, and that the orbit must therefore shrink, slowly, inexorably, on a schedule the equations state to the decimal. No instrument on Earth in 1974 could hope to feel the waves themselves. But the pulsar's own ticks could reveal the shrinkage, if anyone had the patience, so Taylor and his colleagues simply timed it, year after year after year, and the orbit obliged. The pair's closest approach arrives earlier, each year, by seconds worth of accumulated drift per decade, and when the measured decay was laid over Einstein's prediction, the curves fit to better than a fraction of a percent, and have gone on fitting for 50 years. It was the first proof gravitational waves exist, indirect but airtight, the energy visibly leaving the system exactly as the ripples required, and it won Hulse and Taylor the Nobel Prize in 1993, the first ever awarded, in essence, for listening to a clock. Every later chapter, the detectors of 2015, the golden collision of our museum, the timing array hum, descends from that patient decade at Arecibo, from the realization that a ticking dead star, timed stubbornly enough, is a laboratory for the deepest physics there is. And the Hulse-Taylor pair itself spirals on tonight, its orbit a few meters tighter than last year, keeping its appointment with a merger 300 million years from now. A slow-motion rehearsal of the kilonovae, conducted in public, one early tick at a time. The universe, generous curator that it is, even furnishes a laboratory where every effect of tonight runs at once, in the same system, permanently, and astronomers regard it as very nearly the most precious object in the sky. It's called the double pulsar. In 2003, radio astronomers found, in the constellation Puppis, something the catalogues had never held before and have never held since, 2 pulsars, both alive, both ticking, orbiting each other. 2 of nature's best clocks, a recycled fast one spinning about 44 times a second, and a slow young one at about once per 2.8 seconds, locked in an orbit so tight the pair would fit comfortably inside our sun, lapping each other every 2.5 hours at speeds of 1,000,000 kilometers per hour. 2 perfect stopwatches thrown around each other in a deep shared well, and every page of tonight's story is written in their timing. The pulses arrive shifted by the orbital motion and slowed cyclically as each clock swings through the deeper parts of the shared well. Gravitational time dilation read directly off the tick stream, twice over. The system's geometry precesses at relativistic rates our solar system couldn't dream of. The orbit's closest approach point swinging around 17 degrees per year, a rate that would take Mercury, the old test case, more than 4,000 years to match. Space-time curvature bends each pulsar's radio beam as it passes its partner, and, in the years after discovery, the theory's most theatrical prediction played out live. One of the 2 pulsars' beams, tilted by the slow tumble of geodetic precession, the gyroscope wheeling effect of moving through curved space-time, swung gradually out of alignment with Earth, its pulses weakening year by year, until in 2008 it disappeared entirely. A lighthouse turned away, expected, if the models hold, to swing back into view in a few decades. An eclipse caused not by anything blocking the light, but by the geometry itself slowly rotating the lamp, and beneath all of it, the deepest signature. The orbit is shrinking. A few millimeters per day, the pair spiraling gently toward their eventual merger some 85 million years from now, and the rate of that shrinkage matches, to within 1/100% the energy the system must lose to gravitational waves, the ripples we met in our museum, radiating outward from the whirling pair like rings from a stirred pond. Every clause of Einstein's theory, the dilation, the precession, the dragging's cousins, the bending, the waves, all of it checked simultaneously in one system by nothing more than counting ticks for 20 years. And the theory has passed every single test to the limit of every instrument. When physicists say general relativity is the best tested theory we own, this modest pair of dead stars in Puppis is a large part of what they mean. The universe built its own laboratory for bent time, staffed it with 2 perfect clocks, and set it ticking where we could hear. All we ever did was listen carefully, which, you may have noticed by now, is how every discovery in tonight's story was made. And because the universe loves a practical joke, its most perfect clocks turn out to have a flaw. Exactly one kind of flaw, and the flaw is the window into the strangest interior in existence. So let's take the detour. It belongs to tonight. Pulsar timing is smooth beyond any machine, the slow, stately lengthening of the period as the star sheds energy, predictable to a hair across decades. Except that occasionally, without warning, a pulsar glitches. The word is the technical term. Astronomers gave up on dignity here, and what it means is this. One day, between one observation and the next, the pulsar is suddenly spinning faster. Not slower, faster. The period abruptly shorter by a few parts in a million, as if the great flywheel had been kicked. And then, over the following weeks and months, it gradually relaxes back toward its old sedate slowing. The Vela pulsar, one of the sky's most watched, does this every few years, and hundreds of glitches have now been logged across the pulsar population. What kicks a spinning mountain of suns flywheel? The leading answer is wonderful, and it comes in 2 parts. The first is that a neutron star's crust, that kilometer of iron crystal armor we've met on other nights, is spinning down along with the beams. But the interior is not obliged to follow, because the interior, squeezed past the point where ordinary matter survives, is believed to be a superfluid matter in a quantum state with exactly 0 viscosity, a sun's worth of frictionless liquid that can keep spinning at its old rate while the crust around it slows, decoupled, storing the difference like a wound spring. And the second part is the release. The superfluid's rotation is carried in quantized whirlpools, countless microscopic vortices threading the star. And when the mismatch between the free-spinning interior and the slowing crust grows too large, the vortices unpin catastrophically all at once, dumping a share of the interior's stored spin into the crust, which lurches forward faster, and the lighthouse beam we're timing 28,000 light-years away skips ahead in its schedule by a millionth of a second. That's a glitch, most likely, a quake of quantum whirlpools inside a dead star felt across the galaxy as a stutter in a clock. Sometimes the crust itself cracks and shifts, a starquake proper, the flywheel settling its shape by a millimeter, and the timing records that too. Think about what this means for a moment. The interior of a neutron star, the densest matter in the visible universe, a place no probe, no light, no information can ever visit directly, publishes its internal weather in the arrival times of radio pulses, and astronomers on a small blue world read the quantum plumbing of an object they will never see to 9 decimal places by noticing that its tick came a millionth of a second early. Even the imperfections of the universe's best clocks are made of physics no laboratory can reach. The flaw is the treasure, the stutter is the message, and somewhere tonight in some catalogue pulsar, the vortices are straining against the crust, and a glitch is coming, and a telescope will catch it, and one more page of the unreachable interior will have been read by patience from the outside. A natural question has probably been forming behind your closing eyes. If 716 per second is the record, why is it the record? Why not 1,000, 2,000 faster? The universe rarely leaves performance on the table, and the answer, or rather the 2 candidate answers, are each lovely enough to earn their place in the night. The first limit is the brute one, breakup. Spin any body fast enough and its equator eventually moves so fast that gravity can no longer hold the surface down. Centrifugal effect matching surface gravity, and the star begins to shed itself into space. For a neutron star's ferocious gravity, that break-even point sits somewhere around 1,500 to 2,000 rotations per second, depending on the exact size and stiffness of the star, which is the remarkable thing, because it means our record holder at 716 is loafing along at only about half of the absolute structural limit. Neutron stars could spin nearly twice as fast before flying apart. And yet, in 60 years of searching across thousands of pulsars, nothing has ever been found even close to the ceiling. The population just stops, well short, as if something gentler than catastrophe were governing the speed limit, and the leading suspect for that something is, delightfully, a character we already know: gravitational waves. Here's the elegant idea. A perfectly smooth, perfectly symmetric spinning body radiates no gravitational waves at all. But give it any asymmetry, any lump, any mountain, and the spinning lump stirs space-time rhythmically, radiating the ripples we've met before. And the radiation costs spin, breaking the star harder the faster it turns. Now recall how smooth a neutron star is. Its gravity crushes topography almost perfectly flat. The tallest mountains on a neutron star are calculated to stand millimeters high, centimeters at most. The smoothest large objects in existence, smoother by far even than the quartz spheres of gravity probe B. And yet even a millimeter of mountain on a body that dents, spinning hundreds of times a second, is enough. The theory suggests that as accretion spins a pulsar up toward the extreme rates, tiny asymmetries, millimeter hills, ripples in the crust, magnetic distortions begin to radiate gravitational waves ever more furiously until the breaking balances the spin-up and the star simply cannot be pushed faster. A thermostat made of space-time ripples capping every flywheel in the universe at roughly the speeds we observe. If that's right, and searches for the continuous hum of spinning neutron stars are running right now in the gravitational wave data, then the record holder in Terzan 5 is not coasting below its limit. It's at its limit, held there, its excess spin bleeding into the fabric of space as a faint, permanent hum, the singing star singing in a second register no radio dish can hear, its high note being answered forever by the quietest instrument there is. The fastest clock in nature may be fast precisely because the universe is breaking it as hard as geometry allows, a top spun to the edge of the rules and pinned there, millimeter mountains and all, humming into the dark. Since we've spent the night at the fast end of the dial, fairness demands a visit to the other end before we close the case, because the family of cosmic clocks has been growing in both directions lately, and the slow cousins are currently among the deepest mysteries in radio astronomy. For 50 years, the rulebook seemed clear. Pulsars tick between about once per second and hundreds of times per second, with the death line waiting below, the slow boundary past which the lighthouse machinery cannot generate its beams, and the star goes dark. The population obeyed. And then the new wide-eyed radio surveys, the same instruments peeling the zone of avoidance and catching fast radio bursts, began finding things that tick wrong. In 2022, a team in South Africa found a pulsar-like object ticking once every 76 seconds, leisurely beyond anything the rulebook allows, a lighthouse turning so slowly it should, by every standard model, be silent. And yet, there it was, pulsing. And that same year, astronomers in Australia announced something stranger still, an object catalogued from an archival survey that switches on for about a minute at a time, blazing as one of the brightest radio sources in the sky, on a repeating schedule of roughly 18 minutes, an 18-minute tick, thousands of times slower than any classical pulsar, from something compact, magnetized and unidentified, with more of these ultra-long period objects turning up since, ticking on schedules of minutes to hours, a whole covert population of slow clocks. The surveys of previous decades were simply never designed to notice. What are they? The honest answer is the anomaly corridor's answer. Nobody securely knows. The leading suspects are our old acquaintances, the magnetars, whose colossal fields might power beams at rotations far below the ordinary deathline, or perhaps highly magnetized white dwarfs playing the pulsar game at their own gentler scale, or something the models haven't drawn yet. The lesson for tonight, though, is already solid, and it's a lovely one. The universe keeps time at more registers than we knew. From the record holder's 716 ticks per second to the 18-minute mystery in the archives, the clockwork spans factors of 1,000,000, the same physics of collapse and rotation and magnetism playing everything from the highest audible note to a slow gong struck 3 times an hour. And the catalogue is visibly incomplete. The slow registers only now being heard because, for half a century, nobody thought to listen longer than a few seconds at a stretch. Somewhere between the shriek in Terzan 5 and the 18-minute gong In registers not yet surveyed, more clocks are ticking tonight, unheard, keeping schedules we haven't imagined, and some future night on this channel will likely owe them its whole story. One more gift of the galactic clocks deserves its plaque before the close, and it's the map maker's gift. Because pulsar ticks don't just tell time, they measure everything they pass through on the way here. And half of what we know about the invisible substance of our galaxy arrives written in the fine print of their arrival times. Here's the trick. A pulse leaves its star as a sharp crack across all radio frequencies at once, but the space between the stars, as our Alpha Centauri night taught, is not perfectly empty. It's a thin haze of free electrons, and radio waves wading through that haze are slowed ever so slightly, the lower frequencies more than the high. So the pulse arrives at Earth smeared, its high notes first, its low notes trailing, sometimes by seconds, and the size of that smear, the dispersion, is a direct count of every electron the pulse swam through on its journey. Each pulsar is thus a plumb line through the galaxy, its dispersion reporting the total electron fog along one specific path, and with thousands of pulsars scattered through the disk. Astronomers have triangulated those paths into full, three-dimensional maps of the Milky Way's invisible interstellar haze. The density of the medium between the stars, charted not by seeing it, which is nearly impossible, but by timing how much it delays the ticking of dead stars behind it. The lighthouse reveals the fog, and the fog reveals more. The pulses twinkle, scintillating as they pass through turbulent clouds, and the twinkling maps the turbulence, the invisible weather of interstellar space, the same medium a light sail or a crude ark would someday have to cross, surveyed tonight continuously by the flickering of clocks. Even the fast radio bursts from our museum night carry the same fine print, their dispersions counting the electrons of intergalactic space itself, whole cosmic censuses of missing matter conducted via the smearing of millisecond flashes from other galaxies. There's a satisfying wholeness in this at the end of a night about timekeeping. The pulsars began in 1967 as a mystery written in timing. They matured into tools that verified bent time itself, and they've ended up as the galaxy's own surveying instruments, their ticks doubling as depth soundings through everything dark and thin and unseeable between here and there. The clocks mapping the very distances that make all the clocks disagree. In a universe where nothing shares a second, it turns out the disagreements themselves, read carefully enough, tell you exactly where everything is. Given clocks this good, scattered freely across the galaxy, you might wonder whether anyone has thought to use them. And the answer is one of tonight's best-kept secrets. Humanity already has, twice, in ways that bracket our whole story rather beautifully. The first use is already flying, and long-time listeners have met it without knowing. Etched into the golden records aboard the Voyager probes, and on the plaques of the pioneers before them, is a spidery diagram, 14 lines radiating from a single point, each line marked with a long binary number. That drawing is a map, and its landmarks are pulsars. Each line points from our solar system toward one specific pulsar, and each binary number records that pulsar's precise period, its tick, the one number that identifies it as surely as a fingerprint, because no two pulsars tick alike. Any finder, in any age, who has discovered the galaxy's clocks for themselves could measure the periods of the pulsars around them, match 14 of them to the numbers on the plate, and triangulate from 14 lines of position the one star the lines converge on, ours. And because every pulsar's period lengthens at its own steady, known rate, the periods engraved on the record double as a timestamp. A finder could compute how much each tick has slowed since the engraving and date the launch to within decades, millions of years from now. The Golden Record's return address, in other words, is written in the universe's own clockwork, 14 dead stars serving as the shared reference any civilization would eventually own. When we sent our first letters into the dark, we signed them in pulsar time. The second use is newer, and it's aboard the space station right now. In 2017 and 18, an experiment called Sextant, riding on an X-ray telescope attached to the station, demonstrated something spaceflight engineers had dreamed about for decades: navigation by pulsar. The problem it solves is real. Every deep space probe we fly today finds its position by radio conversation with Earth. Whole antenna networks devoted to asking each spacecraft where it is, a system that grows slower and fainter with every billion kilometers, as our Alpha Centauri night made vivid. But millisecond pulsars flash in X-rays as well as radio, and their ticks are so regular that they function exactly like the satellite clocks of the global positioning system, except placed by nature, thousands of light years apart, visible from anywhere, unjammable, eternal. The experiment watched a handful of millisecond pulsars, compared the arrival times of their X-ray ticks against the predicted schedule, and worked out the station's position in orbit, all on its own, no ground contact, to within about 10 kilometers, a first in history. 10 kilometers sounds coarse beside your phone's few meters, but your phone is 30 years and billions of dollars of refinement downstream of its own first demonstration, and the principle now stands proven. A spacecraft anywhere in the solar system or far beyond it can fix its position by the galaxy's own beacons. A positioning system that requires launching nothing, maintaining nothing, and trusting nothing except that dead stars keep their habits, which, as tonight has established, they do to 9 decimal places. Some future craft on the long crossings we once mourned as impossible will steer by exactly these stars the way sailors steered by the fixed ones, and there is a fine symmetry waiting there. The objects that taught our species that time is not universal will be the objects by which we finally keep time across the distances that make it so. And the grandest use of the galactic clocks, the one we glimpsed in the museum and can now appreciate properly, deserves its closing minute, because it may be the most audacious instrument concept our species has ever operated. Take everything tonight has established. The millisecond pulsars are clocks of near-perfect stability scattered across thousands of light years, their ticks arriving at Earth on schedules predictable to hundreds of nanoseconds. Now, suppose space-time itself, the medium the ticks travel through, is not still. Suppose the long, slow gravitational waves from supermassive black hole pairs. The deep ocean swell we met on our museum night are perpetually passing through the galaxy, stretching and squeezing the space between us and every pulsar by parts in a million billion. Each passing swell would make every pulsar's ticks arrive very slightly early, then very slightly late, on rhythms lasting years, and, crucially, the pattern of earliness and lateness across the sky would be correlated, pulsars in one direction running ahead while those in another lag, in the specific quadrupolar fingerprint that only gravitational waves can write. So, the timing teams did the audacious thing. They stopped treating their pulsars as separate clocks and started treating them as one instrument, an array, dozens of the best millisecond pulsars monitored together for decades, the whole ensemble functioning as a single detector with arms thousands of light years long, a telescope whose lenses are dead stars and whose optical path is the galaxy. It took 20 years of data before the instrument reached its sensitivity, and in 2023, as we saw among the exhibits, the fingerprint emerged, the correlated sway, the background swell of the universe's heaviest collisions, heard by an apparatus no one built, only organized. Sit with the scale of that as the night winds down. Humanity's largest scientific instrument is not a dish or a ring or a laser. It is a constellation of spinning corpses distributed by supernovae across the spiral arms, calibrated by their own physics, joined into one detector by nothing more than patient bookkeeping on a small world that learned to read them. We didn't manufacture a single component of it. The universe built the instrument, wound its clocks and scattered them, and all our species contributed was the noticing, decades of it, tick after tick after tick. Every era of tonight's story ends the same way, and this is where it was always heading. First, the clocks taught us time. Then, they taught us where we are. Now, they've become our ears against the deepest sounds there are, and they were all, every one of them, just scruff on chart paper once, half an inch of ink that a patient young astronomer declined to ignore. It's worth setting our species' own clockmaking beside nature's for a few minutes, because the human half of tonight's story is its own quiet epic, and it makes the pulsar's perfection feel earned rather than merely given. Consider how recently we were bad at this. For nearly all of history, humanity's finest timekeepers drifted by minutes per day. Sundials, water clocks, candle clocks, the church tower mechanisms that had to be reset at every noon. The first great leap was the pendulum, in the 1650s taming the day's error to seconds, and the second leap was forced by an emergency of navigation, The longitude problem. The fact that a ship's east-west position requires knowing the time back home, and every clock of the 1700s fell apart at sea. The British government posted a fortune as a prize, and a self-taught Yorkshire carpenter named John Harrison spent, in one of history's great obsessions, over 40 years building the marine chronometers that finally kept faithful time on a heaving deck, clocks accurate to a fraction of a second per day, which won him the money grudgingly and changed the world's maps forever. Notice the shape of that story, decades of one stubborn craftsman's life to gain a factor of 100. And notice that we've met it before tonight in the 40 years of Gravity Probe B, and it repeats through the whole lineage. Quartz, in the 1920s, brought the error down to seconds per year. The cesium atomic clocks of the 1950s brought it to seconds per thousands of years and redefined the second itself. Today's optical lattice clocks, the ones that caught the 33-centimeter staircase, drift by less than a second across the age of the universe, and each rung of that ladder cost brilliant careers, national laboratories, decades. 3.5 centuries of relentless human effort, from Harrison's workshop to the Colorado tabletop, to build a clock worthy of the phrase perfect time. And then in 1967, in the middle of that climb, a graduate student's chart paper revealed that the universe had been running clocks of comparable and over long spans, superior stability all along, billions of them, for billions of years, made not by care, but by catastrophe, wound by collapse, stabilized by sheer mass, distributed freely through every galaxy. There's a version of that discovery that reads as deflating, nature effortlessly holding the trophy our species spent centuries chasing. But the working truth turned out to be the opposite, and it's one of tonight's best facts. The two lineages needed each other. A pulsar without a good atomic clock is just a flicker. You cannot discover that nature keeps perfect time unless you've already built perfect time to compare it against. Every microsecond of pulsar science rests on the cesium standards ticking in basements on Earth. And the atomic clocks, in turn, gained their grandest purpose in the comparison, becoming the reference against which dead stars across the galaxy are audited. The Carpenter's lineage and the supernova's lineage, 3 centuries of workshop patience meeting billions of years of stellar physics. And the meeting point is a timing residual of a few hundred nanoseconds, the thickness of disagreement between the best clock humanity can build and the best clock the universe can make. We built our way, tick by tick, into a conversation with the galaxy's own timekeeping, and we did it in the same handful of decades tonight's whole science fits inside. Whatever else our species gets wrong, it learned to keep time with dead stars, starting from candle marks in 350 years. There's a modern instrument that belongs in tonight's story for one reason above all the others, and it's the reason that sounds most like magic. Since 2017, bolted to the outside of the space station, a telescope called NICER has been staring at neutron stars in X-rays, watching the hot spots at their magnetic poles sweep around with the rotation hundreds of times a second, and from the precise shape of those sweeping flickers, its teams have done something unprecedented. They have measured the actual size of neutron stars, the true radius of the city-sized suns, settling decades of argument about how squeezed the matter inside really is. But the measurement works. And this is the part for tonight. Only because of bent light, and it produces the single most disorienting fact in the whole neutron star catalogue. A neutron star's gravity curves the space around it so severely that light leaving the far side, the side facing away from you, is bent around the star's edge and delivered to your eyes. Stand looking at a neutron star and you do not see half of it the way you see half of every ball you've ever looked at. You see well over half, 60, 70% or more of the entire surface at once, the back of the object wrapped visibly around its own edges, as if the star were turning itself slightly inside out for your inspection. On the most compact models, the bending approaches the point where the whole surface edges toward view at once, every pole and both hemispheres smeared around the disk in a physically honest, impossible portrait. The hot spots, nicer times, are therefore visible even when they've rotated behind the star, their flickers bent around the limb, and it's precisely the depth of that light bending encoded in the flicker shapes that betrays the star's compactness and hands over the radius. Sit with the strangeness of that method. We measured the size of objects 25 kilometers wide and thousands of light years away by exploiting the fact that they bend their own image around themselves, geometries so warped that hiding behind the star is not fully possible, the wells so deep that even the concept of the far side has half dissolved. On our black hole night, we saw the end point of this, the photon sphere, light orbiting in closed circles, the portrait becoming a ring around an absence. The neutron star, once again the visible sibling, stops just short and shows us the almost version, a star you can nearly see all of, all at once, from one side, its geometry folded toward you like a map creased by gravity. Time is not the only thing the deep wells bend. They bend seeing itself, and tonight's clocks live in places where looking at them means looking partway around them, which may be the finest single image the night has offered, a star that cannot quite turn its back on anyone. Before the night winds toward its close, tonight's subject deserves to be set beside its darker sibling one time, because everything we've watched the spinning star do to space and time, the black hole does more, and the comparison illuminates both. Take the whirlpool claws and turn the mass dial past the neutron star's limit, collapse the spinning body out of the universe entirely, and frame dragging does not disappear with the surface. It intensifies and it acquires an edge. Around every spinning black hole, the mathematics draws a region called the ergosphere, a flattened zone outside the horizon proper, and its defining property is the end point of everything tonight has been building. Inside the ergosphere, the dragging of space becomes absolute, not strong, absolute. The current of the whirlpool exceeds the speed of light's ability to swim against it, and therefore nothing, no engine, no photon, no possible effort can hold still there. Hovering ceases to be difficult and becomes forbidden. Motion in the direction of the spin becomes as mandatory as falling, and every object, every light beam, every conceivable thing inside that zone must orbit, full stop, the way everything in tonight's gentler whirlpools merely preferred to. The remarkable detail is that the ergosphere lies outside the horizon. Escape is still possible from within it, and in 1969 the physicist Roger Penrose, a friend of this channel from other nights, showed that a clever visitor could exploit that, dipping into the ergosphere, splitting a payload, dropping half against the spin and escaping with the other half moving faster than it arrived, carrying away in its added energy a sliver of the black hole's rotation. Energy mined from spinning space-time itself, the whirlpool as a reservoir. And astrophysicists believe nature runs some version of this trick at grand scale, spinning black holes powering the great jets we met in the museum, their stolen rotation flung across galaxies as beams of light-speed matter. The pulsar and the black hole are thus two exhibits of one phenomenon. The black hole is the stronger case and the blinder one, its dragging hidden behind a horizon, inferred from orbits and jets and ripples. The neutron star is the weaker case and the visible one, the whirlpool with the lighthouse still burning at its center, the one place the universe lets us watch a stirred space-time and time its consequences tick by tick. Astronomers sometimes call neutron stars the black holes that failed, one collapse short of the abyss. Tonight suggests the kinder framing. They're the black holes that stayed, the ones that kept their surfaces and their voices, the whirlpools that still sing, and nearly everything we actually know, as opposed to infer about matter and time at gravity's edge, we learned because these particular monsters remained visible and kept, of all things, impeccable time. And because no night about bent time would be complete without it, let's say the words the whole subject whispers, time travel, and treat them with the same honesty we've given everything else, because the real answer is stranger than the fiction and considerably more available. Start with the half that is simply, boringly true. Travel to the future is real, permitted, demonstrated, and continuous. Time dilation is a one-way conveyor toward tomorrow. Every fast trip and every stay in a gravity well shifts your clock relative to the world's, and when you rejoin the others, you arrive having aged less, which is to say, you have traveled into their future by the difference. The record holder among humans is a cosmonaut, Sergei Krikalev, who across some 800 days in orbit accumulated a net shift of about 1/50th of a second, arriving home, quite literally, a fraction of a heartbeat further into the future than if he'd stayed on the ground, the most time-traveled human who has ever lived. A 50th of a second is a modest itinerary, but the principle scales without limit. Park a ship in a tight orbit close to a neutron star in the deep of the well we visited tonight, and the exchange rate does the rest. Spend what your clocks call 4 years there. Come home to a solar system that has spent 5. The neutron star is, among everything else it has been tonight, a working time machine, destination future, fare payable in fuel and courage, and nothing about it violates a single law. This is simply what the geometry sells. The future is open for travel and always has been, at every scale from the cosmonaut's 50th of a second to the wildest relativistic itineraries, one direction only, no returns. Which brings us to the other half, the past, and here the honest news is that the door appears closed, but the fascinating news is how it's closed, because the equations, read naively, contain loopholes, and the most famous loophole belongs, of all things, to tonight's own effect. In 1974, the physicist Frank Tipler worked through what extreme frame dragging could do and showed that around an infinitely long, absurdly dense cylinder, spinning near light speed, the dragging of space-time becomes so severe that the whirlpool tips over, so to speak, dragging the time direction itself around into a loop, creating paths through space-time that circle back to their own past, closed, time-like curves, trajectories along which a patient traveler could, in principle, arrive before they left. Frame dragging, the gentle carousel of tonight pushed to a mathematical extreme, becomes a time machine, on paper. The catch, and physicists believe it's the deepest kind of catch, is in the ingredients. Infinitely long, the theorems suggest a finite cylinder won't do without matter of impossible properties, the same forbidden stock we priced on our warp drive night, and the wider judgment of the field articulated in Hawking's puckishly named chronology protection conjecture is that the universe's laws conspire, wherever such loops threaten to form, to slam the door, though a formal proof awaits the marriage of gravity and quantum theory we've noted is still unwritten. So the scoreboard reads like this: futureward travel, open, tested, priced by the geometry, with tonight's neutron stars among the best vehicles in principle ever found. Pastward travel, apparently forbidden, guarded not by decree, but by the requirements growing impossible precisely as the destination approaches, the universe protecting its own history with the same quiet firmness it uses everywhere else. You may sleep tonight in a cosmos where tomorrow is reachable at any rate you're willing to pay for, and yesterday is locked, and both of those, tonight suggests, are mercies. And now, with all the machinery of the night behind us, we can afford the quiet question underneath it, the one this subject always raises at 3 in the morning. If every clock keeps its own time, if the seconds genuinely differ from pole to equator and pillow to ceiling, then what happens to now? What happens to the simple, load-bearing idea that there is a present moment, one universal tonight, shared by you and the singing star and everything between? Physics answered this a century ago, and the answer is the strangest, gentle fact I know. There isn't one. Now is local. Your present moment is perfectly real, but it is yours, defined here, along your particular world line. And the universe simply does not maintain a master present that everyone occupies together. For events far apart, the question which happened first can genuinely lack a single answer. Different travelers moving differently will disagree, and all of them will be right, because the ordering of distant events is, within limits, a matter of perspective, like left and right, not a fact of the world. Relativity of simultaneity, the textbooks call it, and its deep consequence is that the universe cannot really be sliced into a stack of universal moments at all. Many physicists take the next step and picture the whole of space-time as simply existing, past, present, and future together. A four-dimensional landscape in which every event sits at its own address. And the flowing present is something each traveler experiences along their path rather than something the cosmos performs in unison. Einstein himself, in the last year of his life, consoling the family of his oldest friend, wrote that for people who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. He meant it as comfort, and whether or not it comforts, it is where the equations point. But here's the reading of all this I want to leave on your nightstand, because it's the true one, and it's kinder than it first sounds. The discovery that time is local is not the discovery that time is broken. It's the discovery that time is intimate. There is no great external metronome against which your hours are audited, no cosmic standard second that your evening is failing to keep. The only time that has ever passed for you is your own proper time, the time along your path, measured by your heart and your clocks and your slow nights. And it is flawless, has always been flawless, cannot be otherwise. The universe's timekeeping turns out to be less like one great station clock and more like an infinity of pocket watches, one per traveler, each perfect, none supreme, agreeing wherever they meet and drifting wherever they part, and yours is in your chest. The pulsar keeps its furious time and is correct. The equator lags the pole, and both are correct. Your head outruns your feet by billionths, and both are correct. Nothing in this universe is running late. Nothing is running fast. Everything is simply running its own line through the geometry. And the seconds you are spending here in the dark, listening, breathing slower, are not being checked against anything, anywhere. They're yours. They were always going to be yours. And whatever the equations say about the great frozen landscape of events, the experience of moving through your own line of it, this hour, this breath, this drowsy edge, is the one thing in all of tonight's physics that no comparison can touch. One last movement before the close, the long view, because these nights always end by asking what time itself will do with tonight's subject. And the answer for the millisecond pulsars is special even by our usual standards. Ordinary pulsars die young as stars go. Their radio life runs on rotation, they spend it quickly, tens of millions of years, and cross the death line into silence, which is why the galaxy's quiet population so outnumbers its lighthouses. But The recycled ones, the spun-up ones, our record holders tribe, are different. Their colossal spin is a deep reservoir, their magnetic fields worn smooth by the long feast that revived them, drain it with exquisite slowness, and the arithmetic of their spin-down stretches their working lives across billions upon billions of years into timescales that rival and exceed the red dwarf eras we visited on our night about being early. Many of the millisecond pulsars ticking tonight will still be ticking when the sun is a cold, black cinder, still ticking through the age of embers, still sweeping their beams through galaxies gone dark and merged and strange among the very last coherent machines the universe operates. Long after the final star forms, long after the last furnace gutters, the galaxy will still be furnished with clocks, thousands of them, spinning in the dark, timing a cosmos that has stopped producing anything new to time. The lighthouses outliving the shipping, the tick continuing after nearly everything worth scheduling has already happened. There's a melancholy in that image, but tonight has taught us to read these things twice, so read it again. Every era we've ever visited on this channel, every future age of embers and archives and slow oceans will inherit free of charge a working network of precision beacons, position and time. The two gifts civilization finds hardest to build, maintained by physics alone, requiring nothing, failing never. Whatever minds exist in the deep future, whatever they've forgotten, however dark their skies, they will be able to know exactly where they are and exactly what time it is, because the universe's early violence happened to manufacture, as a byproduct, the finest clocks that will ever exist, and wound them for 100 billion years. The first ones awake, if that's what we are, get the view. The last ones awake get the clocks. The universe, it seems, never sends any of its children to bed without a night light. And now, before the folding up, one last small journey, the smallest of the whole night. We've crossed light years and eras tonight, so to finish, let's cross a single second, 1 second. The very interval tonight has been quietly dismantling, spent in full at the record holder. Begin. In the first instant, the star completes its first rotation, all of it, the entire sun and a half of matter around and back, and its beam has already crossed our line of sight. The first tick delivered. By the time your heart, resting, has moved 1/10 of the way toward its next beat, the star has turned 70 times. The beam, out at the light cylinder, has swept its great circle 70 times. The wind has carried 70 pulses worth of rotation into the nebula, and in the crust, the millimeter mountains have circled the star's own sky 70 times, humming their faint permanent chord into space-time. Halfway through the second now, 358 rotations. In this half-second, the equator has traveled 35,000 kilometers, nearly the circumference of the Earth, and every atom in it has aged, by the polar clocks, fractionally less than the atoms at the poles. The star's interior gradient of Wen's deepening by another immeasurable sliver, as it has every second for billions of years. The superfluid vortices, the quantum whirlpools of the interior, have held their pinning. This second, no glitch tonight, though somewhere in the galaxy, statistically, some pulsar's crust is close. Around the star, space itself has been stirred through hundreds of full circulations, the local carousel wheeling at frequencies your ears would hear as a low battle hum beneath the star's high note. And 28,000 light-years away on a small blue world, radio dishes have counted, if they're watching tonight, 716 ticks on schedule, each one dated and filed. Another second of the archive, and the second ends. Nothing happened by the star's standards. It was a Tuesday, quiet second in a life of 10 billion trillion seconds, indistinguishable from the one before, and yet packed inside it were 716 sunrises worth of rotation, a planet's width of travel, a permanent gravitational hum, and one more microscopic installment of the slow divergence between its time and yours. That's what a second is in the deep places, not a tick of the universal clock. There is none. Just an agreed-upon length of becoming, and how much becoming fits inside one depends entirely on where you're standing. In yours just now, a breath went out, and this sentence happened, and somewhere behind your eyes the day loosened another notch. That's a full second too. The universe prices them all the same, which is to say, it doesn't price them at all. It just spends them everywhere, each at the local rate, and lets every sleeper and every singing star keep their own accounts. Now, as we finally come to the end of tonight's long meditation on the clock, let's walk back through it once, softly, gathering the pieces. We began beside your bedside clock, ticking its confident universal tick, and we ended knowing the confidence was a beautiful local habit. We met the record holder in Terzan 5, the city-sized sun singing its high note 716 times a second, equator racing at a quarter of light speed, younger at its middle than at its poles. We learned what a clock really is, counted repetition and nothing more, and how a patent clerk's 2 insights dissolved the master metronome, and how your phone corrects for bent time every time it finds you a coffee shop. We watched Jocelyn Bell find the scruff that became the pulsars, watched dead stars drink their partners and wake up singing, and met the whirlpool claws of Lenz and Thirring, the discovery that spin is contagious, that a rotating mass wheels the very directions around itself. We followed the 40-year patience of gravity probe B and its 40-atom spheres to the proof that our own Earth stirs its surrounding space, once per 35 million years, a carousel you are riding at this moment. We stood off the singing star and watched hovering become impossible, watched 3 perfect clocks disagree perfectly, and came home by way of a Colorado tabletop, where 33 centimeters of altitude measurably changed the speed of time. We visited the double pulsar, the universe's own relativity laboratory, heard the glitches that broadcast the quantum interior, learned why the fastest top in existence may be braked by ripples in space-time itself, and glimpsed the dark sibling, the whirlpool with no lighthouse, mining rotation from geometry behind its closed horizon. And we ended with the pocket watches, infinity of them, one per traveler, none supreme, and the strange, durable comfort that nothing in this universe has ever run late. So here is tonight's ending, and it's a gentle inversion, which by now is this channel's favorite shape. You came into tonight owning, or believing you owned, the ordinary kind of time, the shared kind, the great river everyone stands in together, and tonight took that away, as honesty required. But look at what you were handed in exchange: your own second, a private, perfect, unauditable second, ticking in your chest at the only rate it has ever needed to keep, requiring no synchronization with any star, owing no debt to any master clock, because there is none, anywhere, and never was. The pulsar in Sagittarius keeps its furious time, and it is not more correct than you. The satellites above your roof keep their corrected time, and they are not more correct than you. The whole universe tonight has shown is a fellowship of unhurried clocks, each faithful only to its own path, and in that fellowship your slow breathing, your lengthening thoughts, the soft blur arriving now at the edges of this voice, are not falling behind anything at all. They are exactly on time by the only clock with jurisdiction. Thank you for spending this hour of your one proper time with me, out among the singing stars and the perfect spheres and the 14-line map sailing into the dark. Somewhere in Sagittarius the note is still holding. Somewhere overhead the carousel is turning, one revolution per 35 million years, carrying your bed gently in the direction of morning. There's no hurry, there's no schedule, there's only your own quiet line through the geometry, and tonight, for the next while, it runs through sleep. Take your time. It has always, only, ever been yours. Good night.